Welcome to this video. In this video, I'll be looking at multiple body systems for physics in a motion context. So here we have a train and a wagon moving across the line. Let's have a look at some questions. Now this particular collection of questions comes from the VCE 2016 physics exam paper, so I thought it was worth recognizing that. So we have here a train consisting of an engine of mass 20 tons, which is 20,000 kilograms rather, towing one wagon of mass 10 tons or 10,000 kilograms. So we have our diagram here. The train accelerates from rest with a constant acceleration of 0.1 of a meter per second squared. We want to calculate the speed of the train after it's moved 20 meters. So let's first of all write down what we have, what we can extract from this information. So the speed is a question mark. It's the final speed after the 20 meters, so it's a v, the final velocity equals question mark. Acceleration is 0.1 of a meter per second. The initial speed is from rest, so it has a u of 0 meters per second. And of course we have a displacement of 20 meters in a straight line, so s equals 20 meters. Now, with this information, most people would be woken up to the idea of using one of the equations of constant acceleration. And we have one here that fits it perfectly. So we have v squared equals u squared plus 2as. So we have a v, a u, an a, and an s, the correct equation. And we're trying to find the v. So simply, when I've got v squared equals u squared plus 2as, I can take the square root of both sides to find the v equals the square root of u squared plus 2as. I can substitute in the values. U was 0, a was 0.1 of a meter per second, and s was 20 meters. Slotting that all in, I come out with a final speed of the train after 20 meters of acceleration of 2 meters per second. Nice, simple, straightforward Unit 2 standard physics question. Let's continue on. The next part. The wagon has a frictional resistance of 2,000 newtons. And we're asked to calculate the tension of the coupling between the engine and the wagon. So here we have our engine, our wagon, and we have a coupling. We want to work out the tension. Now, first of all, the tension is between the two. As a result, we can't consider the whole system. We just can't use F equals ma for the whole combination of this system. It won't work. So students quite often get stuck when we're looking at forces between multiple bodies. Do we analyse the engine only, or do we analyse the wagon only? So let's consider both possibilities. If we're going to consider the engine only, we know, even though it's not stated, we know there's some kind of driving force from the engine, the steam engine that's pushing it forward. We know it's accelerating to the left, so there's a net force going to the left. We know there's some kind of friction opposing it. After all, there's a wagon friction being stated, so we know there must be a train or an engine friction as well. And we know that that coupling, from the engine's perspective, is producing a tension pulling to the right. As far as the engine is concerned, this coupling is being slowed down because of force as a result of the friction, etc., that's on the wagon here. So if we ignore the wagon and consider the engine only, it's experiencing a pulling force to the right due to the tension of the wagon. So let's fill in some results. Now, equation-wise, we know that F equals ma. Now, looking at our diagram, we can see that the blue arrow, the driving force, is winning in the direction of the net force. Now, I say winning because it must be larger than the sum of these two to have a net force that's pushing to the left, which is the direction of acceleration. So F equals ma. Now, looking at this diagram, that results in the driving force minus the two red forces here going backwards to the right, the friction and the tension. Okay, so the net force on the engine, it had a mass of 20,000 kilograms and an acceleration of 0.1 of a meter per second. That comes out to 2,000 newtons. However, we still have these three other forces that we just don't have information about. So at this point, we can't solve this. We've got one equation with three unknowns. We can't solve it using the engine as the focus. Let's turn our attention to the wagon. Now the wagon is a lot more simple. If we ignore the engine, the wagon, it is also experiencing a net force because it's accelerating to the left. That's being generated by the tension that's being pulled by the engine. So as far as the wagon is concerned, the tension in that coupling is pulling it to the left. It's generating the force to the left. It's also being opposed by the friction to the right, which we know is 2,000 newtons. So let's look at this as an equation. We know that the net force to the left is the product of the mass times acceleration. And it's equal to, if you like, the tug of war of the blue to the left and the red to the right. So the tension is pulling to the left and the friction of the system is pulling to the right. So the mass of the wagon was 10,000 kilograms. Its acceleration was 0.1. So it comes out to a net force of 1,000. The net force to the left is 1,000 newtons. And it's the result of your tension take away your friction, which means my friction must be 1,000 newtons greater than the friction. Sorry, the tension must be 1,000 newtons greater than the friction of 2,000. So in total, the force of the tension must be 3,000 newtons to the left. When I oppose that and take away the 2,000, that gives me a net force of 1,000 to the left. Let's have a look now. In another situation, the engine as mass 20 tons and moving at 3 meters per second collides with a stationary wagon of mass 10 tons and couples with it as shown. Now we want to calculate the speed of the engine and the wagon after the collision. So let's look at this. It moves in, it collides, it couples, and it moves off. So let's look at this in a momentum angle. Poor choice of words. A momentum scenario. Whenever we're given masses and velocities, you should start thinking momentum as a first option. Now we know in a system like this, where we're just looking at an engine and a wagon, in what we call an isolated system, we're not worried about other objects in the system, the momentum is going to be conserved. So let's have a look. First of all, the momentum before the collision. So before the collision, we have the momentum of the engine. So it's the mass of the engine times the initial velocity of the moment of the engine, rather. And we also have the momentum of the wagon. So it's mass of the wagon multiplied by the initial speed of the wagon, because we know momentum is mass times velocity. We're using u's here to kind of depict the initial conditions. So the mass is 20,000 kilograms. It has an initial velocity of 3. The wagon is 10,000 kilograms with an initial velocity of 0, which means the wagon contributes absolutely no momentum. 10,000 times 0 gives me 0. So in total, the momentum before is coming all from the engine, and it's 60,000 kilogram meters per second. Now, once they couple together, let's look at the momentum after. The momentum after is the mass of the engine and its final velocity v, plus the mass of the wagon multiplied by its final velocity v. However, because they're coupled, it's easier to consider the combined mass multiplied by the combined velocity, because when they're moving coupled, they're moving exactly the same speed. So this is an easier way to do it when we have a combined or a coupled system. So the combined mass is 20 ton plus 10 ton, which gives us 30,000 kilograms, multiplied by a combined velocity. As I mentioned earlier, momentum is always conserved in an isolated system. So the momentum before this interaction or collision or coupling is equal to the momentum after. Momentum before was 60,000 kilogram meters per second, and the momentum after was 30,000 times v. So it's very easy to divide both sides by 30,000 to find that the velocity of this coupled system is in fact 2 meters per second after the collision. Now the next question asks us to determine whether the collision described in the previous question was elastic or inelastic. Now most students will know that for a collision to be elastic, the kinetic energy must be conserved. Now this isn't the case with all collisions. Whilst momentum is always conserved in an isolated system, the kinetic energy isn't necessarily conserved. In fact, it's very rarely conserved. So let's have a look. There's our movement. So first of all, the kinetic energy before the collision. It's the individual kinetic energy of both vehicles. So first of all, it's half mv squared is the equation of kinetic energy. Half the mass of the engine times its initial velocity squared, plus that of the wagon, half mass of the wagon times its initial velocity squared. So it was 20,000 kilograms for the mass of the engine, and it initially had a velocity of 3 meters per second. The wagon has an initial mass of 10,000, and it's stationary, so it has initial speed of 0. Again, it's not contributing anything to the initial kinetic energy. So if we have a half of 20,000, which is 10,000, multiplied by 3 squared, 9, that gives me 90,000 joules of kinetic energy before the collision. Now, after the collision, we consider the kinetic energy of the engine and the kinetic energy of the wagon. Or, as we did with the momentum, we can consider the whole thing combined, which is an easier way to go once it's coupled together. So we have the combined mass multiplied by the common combined velocity squared, and also multiplied by a half. Sub in our values, combined mass is 30 ton or 30,000 30,000 kilograms, and the combined velocity was 2 meters per second. So half of 30,000 times 2 squared gives us a value of 60,000 joules. So to summarize, let's compare. The kinetic energy before the collision was 90,000 joules. Kinetic energy after the collision is 60,000 joules. It's dropped 30,000 joules. So this collision is classified as inelastic because the kinetic energy after collision is less than the kinetic energy before the collision. It's an inelastic collision. That 30,000 joules, by the way, has dissipated probably as heat and friction. Maybe some sound as well. Now finally, in another situation, the engine of mass 20 tons moving to the right at 2 meters per second collides but does not couple with the stationary wagon of mass 10 ton. After the collision, the wagon moves off to the right at 2 meters per second. We want to calculate the velocity, that is both the magnitude and the direction of the engine after the collision. So it comes in, it hits, and then they both move off at different velocities. We want to work out what's the velocity of the engine after the collision. So again, momentum. Momentum before, we find mass of the engine times the initial speed of the engine plus the momentum of the wagon, mass of the wagon, initial velocity of the wagon. So 20 ton, 20,000 kilograms, coming in at 2 meters per second, and the wagon has 10,000 ton and no velocity. So all the momentum is coming from the engine. So that gives us an initial momentum of 40,000 kilogram meters per second. Similarly, after the collision. Now the momentum after, we have the momentum of the engine, its mass times its final velocity, and the momentum of the wagon, its mass times its final velocity. Note these two objects are no longer coupled. This is not a system. We can't combine them together. We have to look at these individually. So the mass of the engine was 20,000 kilograms, and we don't know its velocity after the collision. That's what we're trying to find. That's our unknown. The mass of the wagon is 10,000 kilograms, and we know its velocity was 2 meters per second. So that's how we can write out the momentum after the collision. So let's solve this particular problem. Momentum before the collision is always equal to momentum after the collision. So before the collision, we had a momentum of 40,000 kilogram meters per second. And after the collision, we had a statement that said 20,000 kilograms multiplied by the velocity of the engine, its final velocity, plus 20,000 kilogram meters per second. Let's group these together, see if we can't finish this. So if we have a look at this, 20,000 plus the velocity of the engine, we make that our subject. It's equal to the 40,000 subtracting the 20,000, which leaves us with a nice 20,000 multiplied by the velocity of the engine is equal to 20,000. Now if we divide both sides by 20,000, we find the velocity of the engine to be 1 meter per second, and it's moving to the right. Thank you for watching this YouTube video on multiple bodies in physics. Of course, if you enjoyed this, please don't forget to like, to share, to comment, and as always, please subscribe. Thanks for watching.